Okay, let's talk about waves in general. There are two different types of waves, transverse waves and longitudinal waves. Now, a longitudinal wave is also called a compressional wave, and that actually makes more sense when we get to the images of them. So a whole bunch of vocabulary here. First of all, transverse wave. That's probably the most familiar thing when we think of with waves. Crest, trough. Amplitude is the height of the wave related to the energy, and it's from the midpoint to the top or the midpoint to the bottom. So that's kind of important. Key thing with this, the other thing vocabulary-wise we need to know off it is wavelength. Wavelength we use the letter lambda for, since W is already used a whole bunch. We use A for amplitude and lambda for wavelength. So that's our familiar wave. Now the key thing to understand with this type of wave is the energy is going this way. And remember, all waves do really is transmit energy. They're not moving particles. The particles do this. So if you're out in the ocean sitting on a wave, you're going to bounce up and down while the energy goes from side to side. You're going to do this. And the energy is going to go from side to side. Now, longitudinal wave is much, much harder to draw. I can demonstrate it better with a slinky in class. But what happens is essentially you have areas where it's real close together, then it spreads out, then it gets real close together again, then it spreads out, then it gets real close together again. Now, terms. This is called a compression. That makes sense. The waves are compressed together. So therefore the term compressional wave makes a lot of sense when you think about this. This is one of those science words I don't think you'll ever use outside of a science class. A rarefaction. The rarefaction is the spread out part where the waves are rare. So that makes the sense. The wavelength is down here. It's from compression to compression, or rarefaction to rarefaction, as long as it contains all the parts of a single wave. Wavelength is kind of self-explanatory. It's the length of one wave. So lambda, length of one wave. Now, a couple things that we will talk about a lot are frequency. Frequency is the number of waves per second. It's the number of anything per second. Waves per second is called a hertz. So 60 hertz would be 60 waves per second. We also have period. Period is denoted with capital T. Frequency is denoted with lowercase f. Period is the number of seconds for one wave. We oftentimes don't say wave, we just said it has a period of so many seconds. Now, it's key to understand that if this is waves per second and that's seconds per wave, they're reciprocals of each other. T is equal to 1 over f, and f is equal to 1 over t. They are simply reciprocals of each other. Key thing to understand, waves transmit energy, and that's really what's happening here. Now, a couple other things that are kind of important. Transverse waves. Transverse waves really contain almost all our different types of waves. Light, ocean waves, microwaves, radar waves, X-rays, all those different things that are like light. The only really longitudinal wave that we deal with all the time is what you're hearing right now. Sound. There is one of the earthquake waves is a longitudinal wave, but we're not really studying that right now. So most are going to be transverse sound. The other term that we see pop up in this is a mechanical wave. A mechanical wave needs a medium. In other words, it has to have something to travel in. And by far the most common mechanical wave is sound. It's not the only one. A water wave. If you don't have water, you don't have water waves. So I mean, that's one of those things that makes sense. So the fact that mechanical is sound wave. Sound will not travel in a vacuum, and that's kind of important. No sound in space. So like if I was trying to record this video in space, this is what you'd hear. Nothing. Okay, a little bit primer on waves to get you ready for life's hard knocks.